The neutral wire and the ground wire serve distinct purposes within an electrical system. The neutral wire carries current back to the source, typically a transformer, and in the United States, it's usually colored white or gray. The voltage between the neutral wire and ground is approximately 120 volts in North America. The ground wire, on the other hand, provides a low resistance path for fault currents to return to the source. It's typically colored green or is bare copper in the US. Ideally, the voltage between the ground wire and ground is 0 volts. A fault current limiter, or FCL, is a protective device designed to limit the amount of current that can flow in a circuit during a fault condition. It achieves this by adding resistance to the circuit. The presence of an FCL can have different effects on the neutral and ground wires. Firstly, regarding the neutral wire, an FCL can increase the voltage drop along the neutral wire. This is because the FCL increases the overall resistance of the circuit. Secondly, concerning the ground wire, an FCL generally has no direct effect on the ground wire's functionality. However, it's crucial that the ground wire is properly connected. If the ground wire has a poor connection, the FCL might not be able to effectively limit fault currents during a fault. When an FCL is used on a branch circuit, there are specific considerations for both the neutral and ground wires. Regarding the neutral wire on a branch circuit, the FCL can increase the voltage drop. However, this increase in voltage drop is often considered an acceptable trade-off because of the enhanced fault current protection that the FCL provides. As for the ground wire on a branch circuit, the FCL does not affect the ground wire's protective function. The ground wire continues to provide a low resistance path for fault currents, ensuring safety. To summarize the key differences between neutral and ground wires, consider the following points. 1. The neutral wire's primary purpose is to carry the return current back to the source, while the ground wire's purpose is to provide a safe path for fault current. 2. The neutral wire is typically colored white or gray, whereas the ground wire is usually green or bare copper. 3. The voltage between the neutral wire and ground is approximately 120 volts, while the ideal voltage between the ground wire and ground is 0 volts. 4. An FCL can increase the voltage drop on the neutral wire, but it has no direct effect on the ground wire, provided the ground wire is properly connected. And 5. Concerning branch circuit protection, an FCL can increase the voltage drop on the neutral wire, but this is often acceptable. The FCL doesn't affect the ground wire's ability to provide fault current protection. Now let's delve deeper into the technical aspects of neutral and ground conductors and the impact of fault current limiters on their performance. We will focus on the North American electrical standards, which are based on the National Electrical Code, or NEC. The neutral conductor, as we establish, is a current-carrying conductor. It completes the circuit by providing a return path for the current to the source, typically the transformer's secondary winding. The NEC mandates specific requirements for neutral conductors, including sizing, insulation, and identification. The sizing of the neutral conductor is crucial to ensure it can handle the expected return current without overheating. In many circuits, the neutral conductor is sized the same as the phase conductors. However, in some cases, the neutral conductor can be reduced in size, particularly in circuits with nonlinear loads where harmonic currents are present. Harmonic currents can significantly increase the current flowing in the neutral conductor, requiring a larger conductor size to prevent overheating and potential fire hazards. The NEC provides specific guidelines in Article 220.61 and 220.20 for calculating neutral conductor size based on the type of load and the presence of harmonic currents. The insulation of the neutral conductor is typically white or gray to provide easy identification. This color coding helps electricians quickly differentiate the neutral conductor from the phase conductors and the ground conductor, ensuring correct wiring and reducing the risk of electrical shock. The NEC requires that neutral conductors be clearly identified at all termination points. The ground conductor, also known as the grounding conductor or equipment grounding conductor, serves a vital safety function. It provides a lower impedance path for fault currents to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly trip and energize the circuit in the event of a fault. The ground conductor is typically green or bare copper, and it's bonded to all metallic enclosures, equipment frames, and non-current carrying metal parts of the electrical system. This bonding ensures that all these metal parts are at the same potential as ground, minimizing the risk of electric shock if a fault occurs. The NEC specifies the minimum size of the ground conductor based on the size of the overcurrent protective device protecting the circuit in Table 250.122. The ground conductor must be large enough to safely carry the maximum fault current that the circuit could experience. The NEC also requires that the ground conductor be continuous and effectively grounded to a grounding electrode system. This grounding electrode system typically consists of ground rods, ground plates, or metal water pipes that are buried in the earth, providing a direct connection to ground. Now let's discuss the impact of fault current limiters on neutral and ground conductors. As mentioned earlier, a fault current limiter is a device that reduces the magnitude of fault current in an electrical system. It does this by introducing impedance, typically in the form of resistance or reactance, into the circuit where fault is detected. This impedance limits the flow of fault current, reducing the stress on electrical equipment and minimizing the risk of damage or injury. Firstly, the effect on the neutral conductor. The primary impact of a fault current limiter on the neutral conductor is an increase in voltage drop. When the FCL introduces impedance into the circuit, it causes a voltage drop across the FCL. This voltage drop is proportional to the amount of current flowing through the FCL and the impedance of the FCL. The increased voltage drop on the neutral conductor can affect the performance of sensitive electronic equipment connected to the circuit. If the voltage drop is too large, it can cause equipment to malfunction or even be damaged. However, in most cases, the increased voltage drop caused by the FCL is considered an acceptable trade-off for the improved fault current protection. Secondly, the effect on the ground conductor. A fault current limiter generally has no direct effect on the ground conductor's ability to provide a low impedance path for fault current. The ground conductor is connected in parallel with the FCL, so it still provides a direct path for fault currents to return to the source. However, it's essential to ensure that the ground conductor is properly sized and installed to handle the maximum fault current that the circuit could experience, even with the FCL in place. The NEC provides specific requirements for ground conductor sizing and installation in Article 250. It is also important to consider the coordination between the FCL and the overcurrent protective devices in the circuit. The FCL should be selected and coordinated with the circuit breakers or fuses to ensure that they operate properly and quickly clear fault currents. The NEC requires that overcurrent protective devices be selected and coordinated to protect against both overload and short circuit conditions. This coordination is essential to ensure the safety and reliability of the electrical system. In summary, the neutral and ground conductors play critical roles in an electrical system. The neutral conductor carries the return current, while the ground conductor provides a low impedance path for fault currents. Fault current limiters can improve the safety and reliability of electrical systems by reducing the magnitude of fault currents. However, it's essential to carefully consider the impact of FCL on both neutral and ground conductors, as well as the coordination between FCL and overcurrent protective devices. Now, let's explore some specific applications and scenarios where fault current limiters are commonly used and how they interact with neutral and ground conductors in these situations. One common application is in industrial facilities with large electrical loads. In these facilities, fault currents can be very high, potentially damaging equipment and posing a safety hazard. FCL can be used to limit the fault current to a level that the equipment can safely withstand. In this scenario, the increased voltage drop on the neutral conductor caused by the FCL should be carefully evaluated to ensure that it doesn't affect the performance of sensitive equipment. The ground conductor must also be properly sized and installed to handle the reduced, but still significant, fault current. Another application is in data centers, where downtime can be extremely costly. FCL can be used to improve the reliability of the electrical system by limiting the impact of faults. This can help prevent widespread outages and ensure that critical equipment continues to operate even during a fault condition. In data centers, it's particularly important to minimize the voltage drop on the neutral conductor, as many electronic devices are sensitive to voltage fluctuations. The ground conductor must also be robust and reliable to provide a safe path for fault current. FCL are also used in renewable energy systems such as solar and wind power installations. These systems often have complex electrical networks with multiple sources of power, which can increase the risk of fault currents. FCL can help protect the equipment and personnel in these systems by limiting the fault current to a safe level. In renewable energy systems, the grounding system is particularly important, as it must provide a reliable path for fault currents from various sources. The NEC provides specific requirements for grounding renewable energy systems in Article 690. In addition to these specific applications, FCL are also used in general commercial and residential electrical systems to improve safety and reliability. They can be particularly beneficial in older electrical systems that may not have been designed to handle the high fault currents that are common today. When installing FCL in any electrical system, it's crucial to follow the manufacturer's instructions in all applicable electrical codes. The FCL must be properly sized for the circuit and coordinated with the overcurrent protective devices. The neutral and ground conductors must also be properly sized and installed to ensure that they can safely handle the expected fault currents. Proper grounding and bonding practices are essential for ensuring the safety and reliability of the electrical system. The NEC provides detailed requirements for grounding and bonding in Article 250. These requirements must be followed carefully to minimize the risk of electric shock and fire. In conclusion, understanding the differences between neutral and ground conductors and the impact of fault current limiters is essential for electrical safety and reliability. By following the NEC guidelines and best practices, electricians and engineers can design and install electrical systems that are both safe and efficient. The careful consideration of neutral and ground conductor sizing, grounding and bonding practices, and the selection and coordination of fault current limiters and overcurrent protective devices are all critical components of a well-designed and properly installed electrical system. Remember to consult with qualified electrical professionals for any electrical work to ensure safety and compliance with all applicable codes and regulations.